So today we'll do one numerical on this acceleration diagram construction of a given problem, and we'll discuss about Coriolis acceleration component. Okay, so as you can see, a question is given and the figure is shown in the right hand side. It shows a slider crank mechanism, and crank OA length is given 200 mm. Connecting rod AB is 600 mm. Distance center of mass from crank end, okay, that is another point D is given, okay, whose location is means AD is given 200 mm. At the instant means at this particular configuration, the crank has an angular velocity of 50 radian per second clockwise, and the angular acceleration is given 800 radian per second square, and we have to calculate velocity of uh, point D and angular velocity of AV, that is the connecting rod, and second bit acceleration of D and angular acceleration of AV. Then we have to find out a point on the connecting rod which has zero acceleration at this particular instant. Okay, so to proceed further, first let us note down the given data. Okay, so mm, given data is given, OA is given, OA is 200 mm, that is 0.2 meter. AV is 600 mm, that is 0.6 meter, and AD is given 200 mm, that is 0.2 meter. Now omega AO is given to you, that is 50 radian per second, and alpha AO is given 800 radian per second square. Okay, now let me draw the configuration once again. Sorry. So this is the virtual circle being completed by the crank. We have the slider here. Let's say this point is O, this is point A, slider is B, and the guided portion we are telling as G. So both O and G are same link. Okay, and the configuration is this angle is given 120 degree, omega is 50 radian per second, angular acceleration alpha 800 radian per second square. Now audio is clear to all of you. So first here, what is the difference in this particular question? Who can tell? We have alpha is also given uh, apart from omega. So remember, in this type of cases, we have to find out both the radial and tangential component of the crank also. When alpha is given, you have to find out the tangential component, because a component have only radial component of acceleration, when it is having a constant angular velocity, means if only omega is given, in that case it will have only the radial component. But if alpha is also given, you have to find out the tangential component also in order to find the total acceleration component. Okay, so remember this. So now, now we can find out VAO, relative velocity of point A with respect to O. So this is our VAO. So how to find VAO? So it is omega AO multiply with the link length OA. So 50 multiply with how much? 0.2. So 10 meter per second. Okay, this is the velocity. Now let us draw the velocity diagram. So construction of velocity diagram. So first me let me draw it, then I will write down the steps. So remember, first step is take one point here O and G representing the same point because O and G are same link here. Okay, and as we know the VAO, so draw a line. Okay, draw a line or a vector OA such that it will represent this VAO by direction and by magnitude with some suitable scale. Clear? First step. Okay. Second step, we know that the slider is only moving in horizontal direction to and fro, isn't it? So to represent its velocity, draw a horizontal line. Okay, means only direction. We don't know the magnitude. Okay, in horizontal direction. Okay. Third step is draw a vector. Okay, which will represent the relative velocity of this point A with respect to B. Okay, so it will be normal to the connecting rod. So draw a line normal to this connecting rod. Okay, so from point A, I will draw a line normal to the connecting rod AB. Okay, so both these lines will intersect here. Let me redraw it. So this is my slider velocity line whose magnitude I don't know, and this is a vector perpendicular to the connecting rod, so they will intersect at this point B. So this component OV will represent velocity of point B with respect to the G, fixed point G, and this component will represent, sorry, direction will be, direction will be, we are writing VAB na, so direction will be towards A. Okay, so this component will give you the VAB. Now you measure this vector AB and OV. So now I'm writing the steps. Okay, so first step is take a point OG, OG, and draw draw vector OA representing VAO in magnitude and direction. In magnitude and direction, direction means parallel to VA with some suitable scale. With some suitable scale. Okay. Now next step, from point G, okay, draw a straight line horizontal, that is straight horizontal line representing V VG, whose magnitude is unknown. Magnitude is unknown. Okay. Third step, from point A, okay, draw a vector, or you can say line, perpendicular to connecting rod AB, representing VAB. Okay. So fourth step is both the lines or vectors will intersect at point B. Okay. Now fifth step is locate. We have to find out this point D also. Okay. This is our point D. So here you locate small d here. Okay. As per the scale. As per the scale means here AD is 200 mm. So and AB is how much? 600 mm. So if you have taken say 1 mm is equal to how much? 10 1 mm is equal to 100 mm. So total AB is 6 centimeter and this is your 2 centimeter. So likewise you have to locate point D here, okay, in the velocity diagram, okay, and you join this line by a dotted line, okay, and this will give you the velocity of point D. Clear? So, here fifth step is locate point D on line AB, okay, on same proportion, on same proportion as it is on AB, okay, and join point O and D. Okay, sixth, velocity of point D, that is VD, is equal to the vector OD. So if you measure it, you'll find it is coming around 8.8 meter per second. What was our V? It was 10. It is 8.8 meter per second. Okay. Now, next step, Measure AB. Measure this vector AB, which will give you the VAB. So it is coming around 5.2 meter per second. You please recheck. Okay. Now measure GB, that represent your VBG, velocity of that slider with respect to the fixed guide G, that is 7.2 meter per second. Okay. Now the angular velocity of AB, we can find, how we will find, using this relation omega AB is equal to VAB by AB. So this is 5.2 as we obtained here, divided by the length, that is 600 mm, or you can say zero point 0.6 meter, always mention in meter. So it is 8.67 radian per second. So all the velocity related data we obtained from the velocity diagram. Okay. Now next task is construction of acceleration diagram. Construction of acceleration diagram. So to draw this, first let me draw it, then I will write down the steps. Okay. Remember, first step is to choose a reference point here. Let it be O dash G dash, or you can name it as O1 G1 as per your reference. Okay, O dash G dash. Then remember here in this case, we have both tangential and radial component. Okay, so first we'll draw the radial component of acceleration. Okay, so draw a dotted line O dash x, okay, representing the radial component of AO. Okay, what will be its magnitude? What is the formula for radial component? It will be B square AO divided by OA, isn't it? So we know the magnitude, and its direction will be parallel to the crank OA. Okay, so you'll get point X. Now from point X, draw a line perpendicular to the crank. Okay, remember, perpendicular to the crank, which will represent the tangential component of AO. Now, how to find out the magnitude of tangential component of acceleration? Alpha is given to you. So alpha multiply with the link length will give you the tangential component. Okay, and its direction is normal to the crank AO. So you'll get point A dash here. Earlier we used to draw directly from O dash to A dash. Okay, but it is not like this in this particular case. Okay, now you join. Okay, now you join O dash A dash. So this will give you the total acceleration component of AO. Okay, so next step, similarly for connecting rod, we need to find out both tangential and radial component. So from point A dash, okay, let me change the color. from point A dash, draw a line, okay, A dash y, okay, that represents the radial component of acceleration, okay, A r b a, okay, A r b a, then and which is parallel to the connecting rod. The magnitude we can find out A r b a, and its direction is parallel to the connecting rod. So we'll find y. Now from point y, draw a line perpendicular to the connecting rod. Okay, draw a line perpendicular to the connecting rod. Okay, whose magnitude we don't know. We know the direction only, which is perpendicular to the connecting rod. So draw it here. So this represents the tangential component of BA. Now from point O dash, draw a straight line, horizontal line, which represents the acceleration component of B with respect to G. So both this line will intersect here at B dash, and this component is acceleration component of B with respect to G, and you will find this point B dash. Now you join them. Okay, so now you join this B dash and A dash. This will give you the total acceleration component of B with respect to A. Okay, am I clear? I'll write down the steps. Okay, now another thing left that we have to find out the acceleration of point D also. Okay, so in order to find that, you have to locate D dash here. How to locate? You locate D dash with the same scale where capital D lies on the capital AB. Okay, so you locate D dash on this line A dash B dash, then you join O dash D dash, then you join O dash D dash, and this will give you the acceleration of point D if you measure it. Okay, so this is the total step. Now we'll write this. So first thing is take a point O dash G dash and draw vector vector O dash x. Okay, O dash is parallel to the crank OA. Okay, to represent ARAO. Okay, whose magnitude is B square AO divided by OA. So V square AO is 10 square divided by OA was 0.2. So it is 500 Nike meter per second square. So as per a scale, we draw first this O dash x. Okay. Next step, from point x, draw x a dash to represent the tangential component of AO. Okay, so what will be its magnitude? Magnitude is alpha AO multiplied with OA. So it is 800 multiplied with 0.2, that is 160 radian per second square. Okay, and direction is perpendicular to OA. So we got x a. Okay, x a dash. Sorry. Okay, so we find point a dash. Now third step, join O dash A dash to obtain the total acceleration component A AO. Clear? Now fourth step was that from point A dash draw A dash Y to represent the radial component of acceleration, that is your ARBA, okay, whose direction is parallel to AB, and magnitude is your B square BA divided by AB, that is B square B ଆମର କେତେ ବାହାରିଥିଲା 5.2 ନାଇଁ କି, so 5.2 square divided by AB କେତେ ଥିଲା ଆମର, AB ଥିଲା 0.6 meter, 0.6, so it will come around 45.1 meter per second square. Okay, so we draw this line A dash Y. Okay, ARBA. Now fifth step is from point Y draw your from point Y draw a YB dash. Okay, YB dash, which is perpendicular to the connecting rod AB. Okay, and magnitude is unknown. YB dash. Okay, and from point G dash draw G dash B dash. Okay, representing A BG. Okay, so both the lines will intersect at point B dash. Okay. Sixth step, locate the point D dash on line A dash B dash to the proportion proportion such that such that your B dash D dash divided by B dash A dash is equal to capital BD by BA. Now you measure this O dash D dash, which will give you the acceleration of point D, and it will be around 372 meter per second square. It may vary as per your scale. Okay, nothing to worry. Procedure should be correct. Now 7, we have also need to find out the angular acceleration of AB. So alpha AB will be equal to the tangential component of BA divided by AB. So it is YB dash divided by AB. So it is 521 divided by 0.6. So it will be around 868 radian per second square. Okay, clockwise. As for this particular configuration. Now it has also been asked to find out a point on the connecting rod which has zero acceleration at this instant. Okay, so how to find point of zero acceleration on connecting rod. Now remember, the usual step is you draw once again the diagram with some suitable scale, okay, representing the connecting rod, okay, and the crank on it. Let's say this is point O, this is point A, this is point B, okay, and here the step is draw a triangle ABE, okay, similar to your A dash B dash O dash, okay, in a fashion same fashion, that is your clockwise, okay, in clockwise direction, okay. Means capital AB is your A dash B dash, then you can take another point E here. So this will be your point E as per the same scale used in the acceleration diagram, A dash B dash O dash, okay. Now you join EA here and hatch this portion, okay. Then the point E on the triangle will give the point of zero acceleration. Only you need to locate this point E here. That's it. Okay. So this is the way to solve acceleration diagram problem of a slider crank mechanism. And this one is a very important problem. Okay, remember, it is very important because here we are taking both the tangential and radial component of connecting rod. Okay, so it is very time consuming affair. You need to practice a lot so that you won't waste much of your time during exam. खाली एटा ड्रॉ करिया तुमको अराउंड 30 minutes ऊपर लगिଯିବ ହେଲା आ जदि practice नथिबो it may take around 45 minutes. Okay, that's why I urge you to practice more and more. I will see your notebook, okay, during the class. Next important aspect is your Coriolis acceleration component. Coriolis acceleration component. Let me write down this in capital. Coriolis. Coriolis. Okay, for your convenience. Now let us draw a mechanism. Let's say this is point A, this is point R, velocity is linear velocity is v here, okay, and omega is the angular velocity, alpha is the angular acceleration. Now here we the point P represents a point on the slider, P on slider, Q is the same point on the rod AR, on AR. Just draw it, then I'll explain. Then we have, let's say after a particular time interval, the rod displays through angle del theta and come to this position. Okay, and here this angle will also be equal to del theta, and it will be omega dash r dash cos del theta. This will be equal to omega dash r dash sin del theta. This will be equal to omega dash r dash. Here, let's say this linear velocity is now v dash, and this will be v dash cos theta. This component will be v dash sin theta. Okay. This component is v dash. The angle is del theta. Now I can write here the acceleration of a moving point, the acceleration of a moving point relative to a fixed body that is fixed coordinate system, coordinate system may have two component acceleration, that is the radial and tangential. Okay. However, in some cases, in some cases, the point may have its motion its motion relative to a relative to a moving body. Okay, that is having moving coordinate system. For example, here actually what it is telling that till now we found the acceleration component of a moving point related to a fixed body. Okay, earlier cases like our slider crank mechanism, but we have certain instances. For example, here we have a slider on a rod AR. The rod is rotating through angle delta and also the slider is moving on the rod. So it is a moving coordinate system. So in this particular case, how to find out the acceleration component? For this we use this Coriolis theorem. Okay, that is the importance of this Coriolis acceleration component. Okay, so for example, we can write, for example, motion of a slider P on a rotating link, okay, following analysis is to investigate the acceleration of that point of that point. Now let mm, a link AR, capital AR, rotates about a fixed point, about a fixed point A on it Let P is a point. P is a point on the slider, on the slider, on the link. Let omega is the angular velocity of the link. Angular velocity of the link. Alpha is the angular acceleration of the link. V is the velocity linear velocity of the slider on the link. R is the radial distance of point P. Radial distance of point P on the slider in a short interval of time del t. Uh, so we'll take say for a short interval of time, let's say del t. Let del theta be the angular displacement. Angular displacement, okay, in outward direction. In outward direction. And after del t, okay, let omega dash is equal to omega plus alpha del t, that is the angular velocity of the link. Angular velocity of link, and v dash will be equal to v plus a del t, okay, that is the linear velocity of the link. Then r dash will be equal to r plus del r, that is the radial distance of slider after del t time interval. Okay, now we need to find out the total acceleration. So first find out acceleration of point P. Acceleration of point P parallel to the link, parallel to AR. So how to find? Now initial velocity of P along AR is equal to BPQ, that is equal to V. Now final velocity of P along AR will be equal to V dash cos del theta minus omega dash R dash sin del theta. From the geometry, if you see here we are taking everything parallel to AR. Okay, so V dash V dash cos del theta, okay, minus omega square R dash sin del theta. Okay, this component, because this is coming downward direction and this one is coming in upward direction, so V dash cos del theta minus omega dash R dash sin del theta we are taking now along this parallel to AR, that's why. Okay, now change in velocity will be how much then? What will be the change in velocity? We have final, we have initial, so change in velocity will be equal to V dash cos del theta minus omega dash R dash sin del theta. Okay, this is final minus initial was V. Okay, this is our change in velocity. Now what about acceleration? Now acceleration of point P along the link AR will be change in velocity divided by time. So V dash cos del theta minus omega dash R dash sin del theta, okay, minus V divided by your time del t. So this is the acceleration of P along AR. Now in the limit, we can say, uh, otherwise we can say, so acceleration of P along AR will be equal to V plus A del t. Okay, cos del theta minus, I am substituting the value of final values. Okay, minus this omega plus alpha del t into R plus del R sin del theta minus V divided by your del t. So if you simplify this, we can write here as b cos del theta plus a del t cos del theta minus omega r sin del theta minus omega del r sin del theta minus of your alpha, mm, sorry, एक second, minus of hmm, minus of alpha del t sin del theta, okay, minus of alpha del t del r sin del theta, okay, minus of b. If you simplify, divided by del t. So in the limit, we can write in the limit del t tends to 0, our cos del theta will be how much? It will be equal to 1, and sin del theta will be equal to del theta. Okay, so from above equation, we can simplify this as v plus a del t minus omega r del theta minus omega del r del theta, okay, minus alpha r del t del theta minus alpha del t del r del theta minus of v, so divided by del t. Now this v get cancel out. Omega del r del theta, omega del r del theta can is 0, being very small. Alpha r del t del theta, alpha r del t del theta, this is tends to 0, and this also tends to 0. So we have left with us a minus omega r del theta by del t. Okay, because a del t by del t get cancel out, it is only a here, and omega r del theta by del t. So this much, which is equal to a minus omega r del theta by del t is what? It is again omega. So we can write this as a minus omega square r. This is the acceleration of point P along AR. Let's say this is equation 1. Now we can represent this as the acceleration of slider along AR. That is the centripetal acceleration component, that is known as centripetal acceleration component. Fine. Next we'll find out one thing important. This equation 1 shows the acceleration of point P along AR in the radially outward direction. In the radially outward direction. And acceleration A will be negative. Remember, A will be negative if slider moves inward. If slider moves inward. Okay. Now the next step is acceleration of point P. Acceleration of point P perpendicular to air. Okay. So similarly, we can write initial velocity of P perpendicular to AR is equal to omega r. Final velocity of P perpendicular to AR is v square sine del theta plus omega dash r dash cos del theta. If you resolve perpendicular to air, you will find out this total component. Now what about change in velocity? Change in velocity, it will be, sorry, v square I'm telling, it should be v dash na, v dash sin del theta plus omega dash r dash cos del theta minus omega r. This is the change in velocity. Now acceleration will be how much? Acceleration of point P perpendicular to AR will be equal to, let me directly use the values of all the dash components. So B plus A del T sin del theta plus omega plus alpha del T R plus del R cos del theta minus omega R, okay, divided by del T. Now in the limit of del T tends to 0, our cos del theta will be equal to 1 and sin del theta will equal to del theta. So acceleration, we can say acceleration of P perpendicular to AR will be equal to V d theta by dt plus omega dr by dt plus r alpha, or we can say it is v omega plus omega v plus r alpha, okay, or we can say it is equal to 2 omega v plus the tangential component, because we know when you wish to find out the tangential component of acceleration, this is the formula r alpha, okay. So this is the final one. Let's say this is equation 2. Now the component 2 omega v is known as the Coriolis acceleration component, it is positive, if both omega and theta are either positive or negative, both. So you can say, so Coriolis component is positive if the link AR rotates clockwise, okay, if the link rotates clockwise and slider moves and slider moves radially outwards. Radially outward. Or you can say link rotates counterclockwise, counterclockwise, and slider moves radially inward. Radially inward. In both these cases, Coriolis component will be positive. Otherwise, it will be negative. So you have to remember this condition. Okay. Now let Q be a point on the link AR, and the link AR immediately, or you can say let Q be a point on the QR such that both uh, P and Q are at the same instant. ମାନେ ପଏଣ୍ଟ ହଉଛି ସେମ୍, ଆମେ କହୁଛୁ P ଟା ହଉଛି ସ୍ଲାଇଡର ରେ ଅଛି, Q ଟା ହଉଛି ଲିଙ୍କ ରେ ଅଛି, that's it. Okay, so the acceleration of E, the acceleration of P will be uh, acceleration parallel to AR plus acceleration perpendicular to AR, equation 1 and 2. So if you sum up them, you will find the total acceleration of point P with respect to the A. So we'll have A minus omega square R, okay, plus 2 omega V plus R alpha, equation 1 and 2. So we can simplify this as A plus R alpha minus omega square R, okay, plus 2 omega V, 2 omega V. So we can say it is equal to A is acceleration of point P relative to Q plus this component is acceleration of Q relative to A plus Coriolis acceleration component. Okay, so means this one 2 omega V is the Coriolis acceleration component. So we can write this as your A dash PQ plus A QA, okay, plus A superscript CR. You can say only A here, okay, no issue. So this is the final component of acceleration of point P with respect to A. Okay, this derivation is very important, and we'll solve another two, three, maybe two example the next class. Then we'll have cleanse construction. Okay, then your module 2 will over. Okay, so up to this is very important. You please go through it and try to redraw of yourself. I'll see your copy. I'll check your copy in the next physical class. Okay.
Yes, sir.